Hello, I am so excited to share this episode of the podcast with Professor Mark Jacobson. Mark is a legend in the world of clean energy and climate change. His early work became the scientific basis for California to regulate its own greenhouse gas emissions, an exemption from federal oversight and jurisdiction. He also he published 100% wind wave solar plan for each state, for each country, and that plan became the backbone for the Green New Deal. He has had a lot of impact. He's also very controversial. We dig into that controversy. We address it head on. Mark has been a mentor to me. I studied under him at Stanford, and it was a great honor to sit back down with Mark and have this conversation. I hope you enjoy. Well, thanks for making time. I really appreciate it.
Yeah, sure.
I know you're pretty busy here.
Well, it's my whole life.
Yeah.
I'm getting used to
it. Yeah. You've been a professor here how long now?
This is my 30th year.
30th year.
Yeah. As
wow.
A professor at Stanford.
How old were you when you first became a professor here?
Well, 58 now, so 28.
28.
Yeah.
That's wild to become a professor at Stanford at 28.
Yeah, it was quite, it was fortunate, very lucky for me, I felt. I mean, it was, of course, a great place to come, but I didn't have no expectation of getting a job. It was after my PhD. So I did a PhD at UCLA in atmospheric sciences. I mean, I've always been interested in trying to understand and solve large-scale air pollution and climate problems. And I was studying air pollution in Los Angeles, and toward the end of my PhD, I was thinking, what should I do? I mean, I was interested ultimately in teaching and doing research, but I was thinking probably do a postdoc first. So maybe at NASA Ames, where they have a good research center. But I just found out by chance there was a job opening in civil and environmental engineering at Stanford. At the time, it was just civil engineering, and it was actually on a topic that I didn't really. It wasn't my main area of research. It was kind of a part area of research. It's called atmospheric transport flows, because it was the fluid mechanics and hydrology group who studies water systems and water flows in particular. We're interested in kind of delving into the atmosphere and looking at atmospheric flows, but I did work a little bit on atmospheric flows at the time, but it was more on atmospheric chemistry and air pollution, but it involved meteorology as well. And I was doing computer modeling of air pollution, which involves computer modeling of flows in the atmosphere. Although
you had built a first of its kind model by that point, or you were in the process of building?
Yeah, so for my PhD dissertation, I developed an air pollution model, which is actually only the third air pollution model in the world at the time. But what I did that was unique was to couple a atmospheric chemical model with an atmospheric dynamical model with feedback between the two through radiation transfer. And that had never been done before, either on the global scale or urban scale. So it was actually the very first.
You connected the physics and the chemistry.
Yeah, I mean, there are a lot of weather prediction models around before then. And there were not a lot, but there were a few atmospheric chemistry models that would use interpolated winds or winds that were predicted previously from a meteorological model and put into a file and then used as inputs to move the chemicals around. But never before had there been a meteorological model coupled with a chemical model with aerosols and gases and radiation transfer, and actually interacting, where not only did the winds move around the chemicals, but the chemicals fed back to the winds by changing the temperatures and through other feedback processes.
And when you created this, you were focused on air pollution and human health and cities and extending people's livelihoods and longevity of life. But you weren't necessarily focused on climate change at that point.
No, well, actually, by the time I started, I was just getting into it because my PhD, which was from 1989 to 1994, I studied air pollution in the Los Angeles basin, so developed a computer model that simulated the gases and particles in particular, and then coupled that with a meteorological model and then coupled them interactively. But at the end of my PhD, I also wrote a grant proposal to the Environmental Protection Agency, who was interested in studying, wanted to study global climate. And so in that project, in that proposal, I proposed to extend this urban air pollution model to the globe, to develop a global model that I could then use to study climate. And it was actually miraculously funded just as I was leaving UCLA. And indeed, I got started. I mean, it was a joint with I wrote in some professors at UCLA, and so it was a collaboration. And I ended up then coupling with the UCLA general circulation model as the feeder, as the model that I then transitioned the urban scale model to a global scale by basically taking the same chemistry and aerosol and radiation codes, and then coupling them instead of with a local scale meteorological model with this global general circulation model, the UCLA general circulation model. And so during that project, I then developed the first model in the world that was coupled with feedback between gases, aerosols, radiation, and meteorology. Feedback in both directions, where the meteorology affected the chemicals, and then the chemicals fed back to the meteorology. So that's when I started studying global climate as well.
I mean, to me, to me, that's like prodigy level. Where I mean, you're pretty young at that point. You're developing first of their kind global weather system models, physics and chemistry of air, and air pollution and climate. All is integrating with itself in this model. You become a professor at Stanford at 28. You've been here 30 years. I mean, that's just incredible. It's Good Will Hunting-esque almost. I mean,
well, thanks, but I mean, my whole career, I mean, it has been designed to try to solve these problems like air pollution and climate change, and through, in the end, clean renewable energy solutions. And so for me, it's more, I'm just happy that I'm in a position where I can actually address these problems because they're so important. I mean, I got into this air pollution because when I was really young, like 13 years old, I was traveling to Los Angeles and San Diego and playing tennis. And it was the air pollution, this was in the 1970s, was so bad, I just, you couldn't see like 3 tennis courts down. And you're breathing when you're running, you choke and your eyes are scratchy, and some people are throwing up on the courts. I just thought, why should people live like this? This is ridiculous. And so I thought, this is a problem I want to solve. And this, I'm just so lucky. Sometimes you get lucky in life in one or two things, and I was just so lucky to be able to get a job where I could, at Stanford as a professor, where I could actually do exactly what I set out to do, is to try to understand and solve these problems, and I had the freedom to be able to do that, to come up with new ideas, to code, to teach classes that I really wanted to teach, and also to help train students. Because most jobs, even research jobs, other than maybe at a university, you're really constrained about what you can do. And you can certainly study certain topics, but not necessarily have that ability to try to not only do the research, but then get the information out to large numbers of people, and to try to educate on a large scale, large numbers of people about the problems and the solutions. And so I was just lucky to get that position. I think that was probably the luckiest things in my life.
Yeah, it's pretty incredible. I'm sure the number of students that you've had over the years is a large number that are out in the world doing positive things, making a difference.
Well, yeah, it took like about 10 years, because actually when I did get the job as a professor, I mean, I did do a lot of research, but I was in the program called Environmental Fluid Mechanics and Hydrology. So anybody who wants to study atmospheric science or air pollution or climate looks at the title of that program and says, they have no idea what it means. and it doesn't necessarily mean anything related to climate or air pollution. And so I didn't really get many students. I had a few students for PhD, but then like 10 years later, in 2004, there were a couple of people in our department that were interested in the atmosphere. There were a couple of people interested in energy. And so what we decided to do is combine forces and create a new program inside the department called Atmosphere Energy to actually make it more visible to outside students, and with the goal of people coming into the program, they would try to understand and solve these large scale problems.
And this was one of the first interdisciplinary graduate level academic programs in the country for climate and renewable energy.
Yeah, as far as I know, it was the only at the time, and still a first, that just focuses on atmosphere and energy. So when I say atmosphere, like weather, climate, air pollution, and then energy we focus on clean renewable energy as opposed to all energy. It's clean renewable energy. But yeah, definitely at the time, there were no other programs that were combining both. And we then focused first on the master's program because that is where we had a lot of students coming in who were interested in master's. It was like a 1-year program nominally, and or 1.5 years sometimes. And there were a lot of students interested in doing that. And we did a test run, and it worked out. A lot of students who were passionate about these topics came in, and this program kind of blossomed. And it was I was excited about it, and that's when we started getting lots of master's students. So since then, we probably had, I think, around over 500 master's student graduates of the program.
Wow.
And including yours truly.
Yeah. Back in the day. Yeah.
And also, then I think 2007, we extended that to an undergraduate program. And we've also had PhD students go through the program. So the program still exists, and I'm still very happy about it.
Yeah, it's pretty cool. I remember it really caught my eye when I was looking for applying to graduate school. It was like, wow, here's this program. It is very focused on climate and clean energy. And it's just everything that I could have hoped for in a master's program. I have a question for you about the models. I heard you say in a debate on YouTube somewhere that the model that you've developed, the global weather system physics and chemistry model, is significantly more intricate or complex than the IPCC models.
Yes.
Can you explain that? And why is that? And why don't they use your model? Or how does the modeling who decides what models to use, and how does that all work?
Right. So just first, yeah, it is more complex. And the reason is because it started as an urban air pollution model. Well, with respect to models, the problem with atmospheric models in general is that they take an enormous amount of computer time. No matter how many supercomputers you have, or even supercomputers linked together, you always need more computer time. So, but air pollution model is very intricate. It's very high resolution in space, but also usually simulations are very short simulations, like 3 or 4 or 5 days, maybe it could be a week simulation. And so you can put in a lot of physics and chemistry, dynamics, radiation, ocean surface processes, land surface processes. So they're very complex. So whereas climate models historically were basically just meteorological models. And a meteorological model, just to put in perspective, of all the computer time in a coupled meteorological air pollution model, the meteorological part generally takes maybe 1% of the computer time.
Wow.
So the chemistry and aerosol microphysics and cloud microphysics in a coupled model are taking 99% plus time. Because you're treating like gas chemistry, which is very nonlinear, and you're trying to solve it exactly in hundreds of thousands to millions of grid points. And then you have particles, what are called aerosol particles, which are larger than gases, but they have different sizes. So you not only have to treat, because gases are basically one size, and you can treat them as one size, but there are like hundreds to thousands of gases that you have to treat their interactions. But particles, they have different sizes. So you have to treat all their sizes. Then each size has a different composition. Then you have a bunch of different chemicals in each size, and then each size is interacting with each other size. And so you have to treat those interactions if you want to do it right. then you have gases interacting with the particles of each size and of each composition. And then you have to move them all around, and then you have to do radiation transfer through all of them. So it's very complicated. And
the chemistry really matters. Like as an example, sulfur dioxide emissions can greatly impact the reflection of sunlight. Various gases do different things in terms of the absorption or reflection of sunlight. And it's not just radiative trapping of greenhouse gases. There's a much more complicated picture around how the Earth warms based on events as it moves forward in time.
Right. Well, there's interaction, especially when you're looking at air pollution. You have thousands of chemicals that are interacting and people breathe them in. And so it's not just, greenhouse gases are pretty inert and they don't really react chemically. That's why they're greenhouse gases. They're long-lasting gases that don't decay chemically over time very easily. So you don't have to really deal with the chemistry at all. But when you're talking about ozone in smog, when you're talking about oxides of nitrogen, oxides of sulfur, oxides of hydrogen, they're all interacting. Hydrocarbons, they're reacting, and on different timescales. Some are like timescales of like 10 to the minus ninth seconds, and others are in timescales of 1 second. Others are in timescales of 100 seconds. So you have to deal with these not only nonlinear equations, but what's called a stiff set of equations, and you need what's called an ordinary differential equation solver that solves stiff equations, and those take an enormous amount of computer time. And that's just the gas chemistry. Then you have all these other processes. But to answer your question, so the climate models have typically ignored all the chemistry, physics of aerosols. Most don't even have aerosols except maybe like a bulk aerosol or something. And then clouds have been so simplified in climate models. And the reason is because to actually finish a simulation, and climate simulations have generally been hundreds of years to sometimes thousands of years. And so you need something that runs really fast. And so they take everything out, that's all the physics, all the major physics out, and they have a lot of parameterization.
To be able to process that much time of the calculations.
Yeah, to be able to actually simulate for over a lot of grid cells worldwide for centuries to thousands of years. So I took an urban model that I built and expanded it to the global scale. And I maintained all of the details. And as a result, it ran very slowly. So when I did climate simulations, in fact, to this day, I've rarely done a climate simulation longer than 50 years. I mean, most of my simulations are short-term climate simulations. And because, I just don't have the computer power. I mean, I could simplify it, but what I've learned is that once you start simplifying by taking things out, you get different answers.
That's what I was going to wonder, like how do people with all of these different approaches, or just these two different approaches, maybe there's more, make sense of truth amidst the, because people aren't necessarily within these models. They don't necessarily understand the details of them or their mechanics or their differences. And the models generally all say, directionally the same thing, but there are important differences, and the differences can create a lack of trust. Even there's sort of it can be politicized. It can be, where you can't trust the models because who knows what's in them.
Yeah. Well, that's true. And now there is an element of that, but the good news is that, so in terms of greenhouse gases, like the effects of greenhouse gases, I mean, I test like my model against other models in terms of greenhouse gas effects. And you do get similar answers in terms of the greenhouse gases compared with other models, because it's such a dominant influence and such a dominant feature. I mean, their impacts are so dominant of greenhouse gases. But what I've focused on are the effects of particles on climate, and that's where you see big differences. And so the particles can be either what we call cooling particles or warming particles. So there are only a couple of real warming particle components, what's called black carbon and brown carbon.
Yeah, soot.
Yeah, which is black carbon is the main component of soot, and brown carbon is also part of soot, but also can be from some other sources. And these, black carbon is black because it absorbs sunlight directly. It then heats the air directly because it takes that sunlight, converts it to heat, and then releases the heat to the air around it. Unlike a greenhouse gas, which is transparent to sunlight, but absorbs infrared radiation emitted by the surface of the Earth. Black carbon also absorbs infrared radiation, but that's its absorption of solar radiation is way more powerful. Just to give an example, like 1 gram of soot, black carbon, in the atmosphere heats up the air about 1 million times more than 1 gram of carbon dioxide.
The air around it. Wow.
But the difference is black carbon and soot only lasts in the atmosphere a few days to a few weeks.
Wow.
Whereas carbon dioxide lasts, has a lifetime of about 80 years on the order. So as a result, you don't have as much, but you always have emissions of black carbon. So you always have a certain amount in the atmosphere. And what I discovered with this model, doing this modeling, is that black carbon may be the second leading cause of global warming after carbon dioxide.
And it lands on glaciers in high mountains, especially in Asia, and it's melting glaciers especially fast.
Yeah, so some of the impacts, aside from absorbing sunlight directly, is that it deposits onto sea ice, snow, any light-colored surfaces. Well, if it's sea ice or snow, it can then melt that sea ice or snow really rapidly, because what happens is it settles on the top of the snow, for example, and then sunlight hits the black carbon heats up and then radiates infrared heat around it to melt the snow really fast. So you can actually put 2 patches of snow, put some powdered black carbon on one, and just leave the other bare, and you'll see within a day or two, the black carbon one melts completely, whereas the other one's untouched.
Right.
But the other impacts are that inside of clouds, black carbon dissipates clouds as well. So you go over like Southeast Asia, where you have this huge amount of soot emissions and organic and brown, what we call brown carbon as well. And over these big cities, you see no more clouds. So you see a lot of haze, because you basically dissipated the clouds, and then the water vapor then kind of condenses onto particles to become haze.
Yeah. So these feedback cycles, you try to render in your model and move forward in time what's going to happen as different inputs change. How do we? I'm gonna jump into actually the waiver system. I'm gonna just because we don't have that much time, so I want to. Your modeling was integral to proving or expert testimony around carbon domes, carbon heat domes around cities, which, similar to everything we've been discussing so far, the physics and the chemistry of all of that led to the waiver of California from the EPA, from the sort of regulation of the U.S. government. And in a sense, it kind of put it outside of the mandate of the Supreme Court, even. Like California can have higher standards of car emissions and regulate its own greenhouse gases as a result of this waiver.
Yeah. So the history behind this is that, well, historically, California has been able to control or to set its own standards for air pollutants that affect people's health. And that is because California, starting in about 1946, well, this Los Angeles Air Pollution Control District was the very first air pollution control district in the United States, and was granted by the state of California to be able to control its own air pollution. And ultimately, ever since then, California has been setting standards, not only in Los Angeles, but then throughout California, has been setting standards for not only like refineries and dumpster emissions and gas station emissions, but tailpipe emissions for vehicles. And the Environmental Protection Agency, which was started in 1970, it has looked to California to California's regulations to set federal regulations. So California has always been a precursor to federal regulations for air pollution, not only ambient standards, outdoor concentrations of pollutants that people are allowed to have, but also like tailpipe emissions.
It's at the vanguard. It sets the trail.
Yeah, it sets the trail. And so there's a lot of testing is done of standards in California, and then they may or may not be adopted at the federal level. So, since the EPA came around, though, the California has always been able to set tougher standards than at the federal level, but generally it's had to request the EPA for a waiver to set tougher standards. And every time it's been granted this waiver. So, but in 2007 or 8, California requested the EPA to be able to control its own tailpipe emissions of carbon dioxide,
which isn't regulated under the Clean Air Act because it doesn't directly affect human health.
Well, that was that was an argument that was made.
Right.
Because the Clean Air Act amendment of 1970, it allows the EPA to control pollutants that affect people's health and welfare. And the argument by some people, a lot of people at the time, was, well, carbon dioxide doesn't affect people's health. It affects climate, but that doesn't necessarily directly affect people's health. And so when California made this request, California was denied the request by the EPA administrator. And the EPA administrator argued that, well, that carbon dioxide doesn't affect people's health, and it would have to show, California would have to show that controlling carbon dioxide would have a better or a greater impact in California than any other state, actually, to excuse me, to get a waiver. And it said it didn't, local emissions of carbon dioxide don't affect people's health.
Mm-hmm. So they were denied the waiver on the premise that there's no differentiation between states in terms of greenhouse gases affecting human health, and then they went to you essentially to with your model to demonstrate that's not the case.
Well, so they were saying that the EPA administrator, and this was under George Bush, was stating that California has to show a special need for the state of California. There has to be like some difference in emissions in California versus another state for California to get a waiver. And they were saying, well, CO2 affects, if it has a climate effect, it affects climate equally everywhere. So there's no special need in California for a waiver. And also, he was saying that CO2 emissions don't affect people's health directly, regardless. So there's no need under that grounds to grant a waiver either.
And that's the cornerstone of regulating of environmental policy in the U.S. is the Clean Air Act.
Yeah, and that's based on
that's the law of the land.
Well, so the administrator at the time was interpreting the Clean Air Act to say that there's no basis for controlling CO2, carbon dioxide, because it doesn't affect California. I mean, giving California a preferential treatment of CO2 because it doesn't affect California more than any other state, and it doesn't have a local effect on people's health. And I coincidentally was working on that topic, and I was, with the model I'd been developing, was looking at two things. What was the effect of carbon dioxide on people's health through changes of temperature? Mm-hmm. And based on that study, I found that, well, carbon dioxide does affect people's health because when it raises the temperature increases ozone in polluted air. Higher temperature increases ozone in polluted air, but it does not increase ozone in non-polluted air. So there's a differential effect, and there's a reason for that. But when you have an already polluted airshed, higher temperatures, even like 1 degree higher, will increase the ozone in that airshed and cause more mortalities and morbidities. Whereas an increase of temperature in a rural area won't increase the low level of ozone to a higher level. And anyway, there was a complicated chemical reason for both of these findings. But it was not only the temperatures, it was also because when you have higher temperatures, you have more water vapor because you evaporate more water from the ground. And the higher water vapor independently increased ozone more in polluted air, but not in clean air. So two effects of carbon dioxide were the higher temperatures and the higher water vapor independently increased ozone, which was a harmful air pollutant that kills people today. And so that was one finding. And then I did a separate paper where I looked at, well, in urban areas, you have elevated carbon dioxide levels because you have more traffic, more sources of CO2, and measurements, like there are measurements in many cities in the US where they actually measure the carbon dioxide levels, and they're like 100 to 200 parts per million higher than the background. The background CO2 is like, today it's like 420 to 425 parts per million. But we're seeing in some cities, 550, 600, 650, 700 parts per million of CO2. So I modeled
Really?
that.
In some cities? I didn't realize that. Wow.
Well, in fact, all the cities that they have measurements, I'm sure all the cities are elevated. But yeah, you get 700 a lot of times.
In some cities, wow.
Yeah. And now CO2, though, does not have it's not going to cause death until maybe 15 to 30,000 parts per million. So it's not going to kill you directly. But what I modeled that impact of those what I called CO2 domes over cities, how they impact local temperatures and how that fed back to ozone and other chemicals. And what I found was those elevated CO2 levels increased temperatures locally, and those higher temperatures and increased water vapor, and those higher temperatures and water vapor then cause more deaths locally. So, and then the third thing is, so California had at the time and still has it was like 8 out of the 10 most polluted cities in the United States. So these findings were that because California already had the most polluted air in the US, higher temperatures in California due to higher global CO2 caused more deaths.
Preferentially more deaths.
Deaths in California than other states.
And therefore it should have the legal right to regulate greenhouse gases.
Yeah, regulate CO2. And also, in addition to that, the local domes were causing increased deaths locally. So the CO2 was causing indirectly, but locally causing more deaths just due to the local emissions of CO2. And so in 2009, when the new administration came in, they had new hearings because California then requested the waiver again. They invited they invited California to submit expert testimony, and California then invited me because they'd seen my papers to testify. Mm-hmm. And in fact, I was the only witness for California, who was a science witness, to testify at the EPA hearings. And so I testified about this, and then I was told that based on these findings, they then granted California the waiver, which was the first. It was really the first law allowing CO2. California's law was the first law allow tailpipe CO2 to be regulated in the world.
This cracked open the door to regulating greenhouse gas emissions in America and beyond, because it's like America looks to California, the rest of the world looks to America, and there is a sort of precedent-setting nature to this whole story, which is why I'm focused on it right now, because I think it's fascinating. Because I think a lot of people don't realize or know any of this and think that there has been no regulation of greenhouse gases or climate, but all of this is how the legal system works and is sort of a backdoor into it, and has been politicized. Like it existed, and then Trump got rid of the waiver, I believe.
Well, he tried to. I don't think he was successful.
Oh, he didn't succeed. Okay.
Yeah, I think he was pushing for it, but I think it was in the courts, and then
they stymied. Okay, for some reason I thought he got rid of it, then Biden put it back in. But either way, and then 40% of other U.S. states have followed California's tailpipe standards via the same waiver system. They've opted into the waiver system.
Yeah, I'm not sure what all the other states have done, but that's generally about 40% of states follow California's tailpipe emission standards. Yeah, in general. So like if California says we are limiting some emissions of any chemical to a certain amount, other states 40% of the other states follow immediately.
Yeah, it's incredible. I mean, and this from your early research as a PhD student at UCLA, the modeling work there, and this leading to, talk about impact. It's
there's another one that actually nobody knows about, which was it was around 2004, because I'd done work on the black carbon I mentioned, finding that black carbon may be the second leading cause of global warming after carbon dioxide, based on its warming effect, not only because it absorbs sunlight and has these effects on snow and clouds, but also because when you coat it with other material, like in the atmosphere, soot particles become coated with other gunk. And when that happens, black carbon actually absorbs more because you get bigger particles, more sunlight hits the particles and bounces around and gets absorbed by the black carbon. So that actually doubles the warming effect. So I found in a paper in 2001 that black carbon may be the second leading cause of global warming. But not only that, because it's a particle, and particles cause 90% of air pollution mortality. And worldwide today, for example, 7.5 million people die every year from air pollution, and 90% of those are from particles. So, black carbon particles are part of those particles that cause death. And
I've read that's like 10 to 11% of global deaths each year is air pollution related.
Yeah, total deaths worldwide. Yeah, it's because
just to contextualize that.
Yeah, it's about 10 or 11%, second leading cause of death worldwide after heart disease. But the particles, because they're short-lived in the atmosphere, if you remove them, if you stop emitting black carbon soot particles, you can have a rapid increase or rapid reduction of climate impacts from the black carbon and a rapid reduction of the health effects. So it's not only the fastest, so controlling black carbon may be the fastest method of actually slowing global warming. Mm-hmm. And so this was a finding that back in 2000, in 2001, and ironically, George Bush II, who became president right after, well, I hadn't published this paper on this, but the White House was asking for papers from the EPA again on climate because he had to decide whether the U.S. would take part in the Kyoto Protocol. And so he asked the EPA, and it turned out I had sent to the EPA this paper on black carbon and just to review. And at the time, then the White House asked the EPA if they had any papers, and they said, we have this paper on black carbon. Would you like it? And so they asked me permission if they could see the paper at the White House. So I said, yeah, that's fine, but please don't cite it or quote it because it hasn't been published yet. And so they said, fine. But sure enough, 2 weeks later, President Bush is giving a speech about why the U.S. is going to pull out of the Kyoto Protocol.
Oh, no. Really?
And so he says, this is a quote. He says, we're pulling out of the Kyoto Protocol for two reasons. One is because it's not fair because China and India don't have to do as much as we would. But the second reason is because it doesn't include black carbon.
Which was not at all your intent, right?
Yeah, and he says, not only that, he says controlling black carbon would not only slow global warming, but improve human health. It's not a reason to pull out of the Kyoto Protocol, it's a reason to improve it.
But that's a fascinating lesson in politics, right? Like, so here's science, you're representing science, and Bush, it became politicized. He used that piece of information in a political nature to justify whatever.
Yeah, after I said, please don't cite it or quote it.
But do you think that can cut both ways? That, like, at the intersection of science and politics is a very fraught territory. And you've existed in this territory.
Well, what I've learned from that is, first of all, policymakers will want to use selective science a lot. They'll select which science they want to follow. But the other thing is, like, if I put information out, I really have to follow up and keep explaining it to people so it doesn't get misinterpreted. Mm-hmm. Because this was a classic case where somebody's like misinterpreting. I mean, fortunately, he actually gave the correct conclusion. So it wasn't he wasn't saying, he was just using it in a contextual way. But you really, as a scientist, you really have to follow through and explain to people your research because most people don't understand a lot of the research. But this was leading to a different story. The good part about that whole thing on black carbon was, so a couple of years later, the California Air Resources Board had to decide whether to allow diesel vehicles, which are ones that emit a lot of black carbon, the smoky soot that comes out of them, whether to allow them to still emit soot. Because they were trying to get it, like California tightened its particle emission standards from vehicles. Mm-hmm. And gasoline vehicles could meet these standards pretty easily, but diesel vehicles could not. And so the diesel vehicle industry was trying to get an exemption from California so they can have higher emissions than gasoline vehicles. But the California Air Resources Board decided that based on the fact that on climate grounds, based on the study that black carbon may be the second leading cause of global warming, that they would not allow diesel vehicles to get an exemption. So as a result then of this paper, and they're also saying diesel particles also cause health effects too, mm-hmm. So that was an additional reason. But because of this paper and the health effects of diesel, you cannot buy a diesel vehicle in California from about 2004 to 2011. Mm-hmm. And in 2011, I think after that, they started putting filters in some of those cars. So that was a good story from the study.
Okay, on people misinterpreting the science, politicians, but also I want to get to to the study in the National Academy of Sciences in 2017 that received a lot of controversy. 100% wind wave solar plan for the country that evolved into plans for all the states, for every country, a whole project, the solutions project that you've worked on with some famous actors, some famous documentary filmmakers, a kind of amazing cadre of climate change advocates trying to affect public policy, trying to make a difference in this area. You came out with a paper that modeled how it would work, what the plan would be, how many gigawatts of solar, megawatts of solar, how many wind turbines, how much land area it would use, how much hydro, like what it would actually look like, what it would cost, how it would affect air quality, how it would reduce costs of negative externalities like people dying, morbidities and mortalities, and just the whole picture. And it was criticized heavily in a later publication, and it seemed like they misunderstood, or they didn't have quite the right insight into what you were doing. Like for instance, one of the things they seemed to mistake was like primary energy versus used energy and use energy. It was like one potential mishap in the whole thing. But I'm just really curious as to your take on that whole experience, because it seemed to be a very difficult experience for you. But
yeah, well, some context. So we had started, my whole career I've been trying to understand and solve these large-scale pollution and climate problems. And until about the year 2000, I've been focusing mostly on the problems, trying to understand the problems. And around the year 2000, I started looking at solutions. So starting with wind energy, I was doing wind energy analyses and looking, for example, how many wind turbines would it take to replace coal in the US. I think that was the first paper we did. Then I had a PhD student starting to do wind resource analyses worldwide based on data. So she published a couple of papers, including a global wind atlas. But fast forward to about 2007, 8, I started getting interested in solar as well and geothermal, and I did a review paper in 2008, which was to analyze what are the because people are proposing all sorts of solutions to climate change at the time, including carbon capture, nuclear power, bioenergy, and in addition to renewables. So I decided to do a review paper because I'd done a lot of work on looking at the impacts on the atmosphere of different fuels like hydrogen, ethanol, coal, natural gas. So I'd done air pollution analyses and some climate analyses of different fuels in addition to working on wind energy. So I decided to do a review paper trying to look agnostically at a bunch of different energy technologies, both for electricity generation and transportation, and also their impacts on the environment, like air pollution, health, on climate, on water, on contamination, but also on reliability and land use and some other parameters. But ignoring cost, because I just want to see, what are of all these technologies, which ones are the best, and which ones are the best for solving these problems that we have, and
including the air pollution component, which is largely missing in a lot of the other strategic views of what the direction forward is for the country.
Yeah, so I'm trying to solve air pollution together with climate and energy security. In fact, that was the title of the paper related to examining energy solutions to air pollution, global warming, and energy security. So those are the three problems we're trying to solve simultaneously. And anyway, long story short, that paper, it concluded that, the best technology is probably the most obvious one, like there's wind, onshore and offshore wind, solar photovoltaics on rooftops and power plants, concentrated solar power, some geothermal, even tidal and wave, again, ignoring costs at the time. And then hydroelectric power came in, it was pretty close, but it has some drawbacks, land requirements, and people don't like the impacts. But then, below that was like nuclear, carbon capture, biofuels. Those came in last. So from this paper, I concluded, the best technologies are what I call wind, water, solar technologies. and which includes basically
WWS. Every time I see WWS in your page, in my mind go WWF, and I think of, and I think of like sort of World Wildlife Fund, are also the like wrestling, like
yeah.
Anyway,
well, wind, water, solar it's short for not only the electricity generators that are clean and renewable, but storage and electrification. But so after that, then I was asked to write a paper on, well, okay, if these are the best technologies, can we actually power the world with these technologies? And so I then partnered with Dr. Mark DeLucchi, who was at UC Davis at the time and is now at Berkeley and Davis. And we wrote a paper in Scientific American basically analyzing, is it possible to power the entire world with just wind, water, solar technologies by 2030? And we looked at the cost in addition to land use and materials and other factors. And the conclusion was, yes, it's technically and economically possible. However, for social and political reasons, it probably won't happen. But maybe getting most by 2030, maybe like 80%, and the rest by 2050 is more likely goal. Little did I know that paper turned out to be the scientific basis for what's called the Green New Deal, which was a policy proposal that came up in around 2018 or so for the U.S. to transition to 100% renewable energy by 2030. But
so just to emphasize that, your paper, your plan is the backbone of the Green New Deal.
Yes.
Yeah. Okay.
Yeah. So then, our paper, the 2009 Scientific American paper, is the scientific basis for the Green New Deal, and that's where the energy portion of the Green New Deal. The Green New Deal also talked about other social issues that are not related to energy, but the energy portion of the Green New Deal. But from there, after that, I did a TED Talk with Stuart Brand, it was a debate actually.
Where I rewatched it. Yeah,
it was he was for nuclear energy, and I talked about why these other technologies are better than nuclear.
The audience was 80-20 pro-nuclear, and at the end it was maybe 60-40. So you successfully swayed at about 20% of the audience to be anti-nuclear.
Yeah, I was happy. I mean, it was happy to be able to switch some people, but it was an interesting dynamic there. But the point of that is, from those two things, that Scientific American article and that TED debate, then I was introduced to some great people who I ended up then starting a nonprofit with, Mark Ruffalo, Marco Krapels, Josh Fox, who, Mark Ruffalo is an actor and activist, but Josh Fox is a filmmaker, and Marco Krapels was a businessman at the time. And we just hit it off at a dinner, and the reason we met was that Mark Ruffalo and Josh Fox were working in New York against fracking, natural gas hydrofracking, which the state of New York was considering because Pennsylvania nearby had a lot of fracking going on.
The movie Gasland, he made the movie Gasland, very famous film. Yeah,
Josh Fox had got a nominee for an Oscar for Gasland, which was really exposed gas hydrofracking, pretty much brought it into the forefront. And so they were looking for, what's an alternative to fracking in New York. And so I developed me and Mark DeLucchi had developed this plan for the world, basically. And they wanted to know, well, can we do something similar for New York? And I thought about it, and I said, well, I know this is going to be a lot of work. And so I told him at this meeting, this was in 2011, in June of 2011, I told him, well, how about I'll write one paragraph, and then you can get somebody else to write the rest. I knew it would take a long time. And it turned out, so they said, okay, well, that's all you can do. So I started writing this paragraph one night, and I got inspired. And I just thought, well, if I want to really solve this problem, I have to be able to do it at the state level too. And so I stayed up all night, and I started basically compressing this world plan into a New York state plan, and kind of found some additional data. Anyway, the next morning I sent them it was like a 14-page draft of a New York energy plan.
Just the next morning after.
Yeah, the next morning.
Oh my God. Were they like, who is this guy? Like, what?
Yeah, well, basically one guy commented, because there was a larger group at this time. It was about 10 people. One guy commented, well, a few more days like this will solve the world's problem.
Yeah. It's pretty productive, yeah.
But, well, it turned out it needed 35 more edits or versions before it finally got published in 2013. But that was the start. I mean, people became inspired because, well, we had a New York energy plan, and then everybody was like really just, we were staying up late and talking a lot. And we were really excited about like bringing this to the state of New York and to the governor, which we ended up doing. And the state of New York eventually not only passed a 50% renewables law in 2015, but went to 100% renewables in the electric power sector. I think it was like 2018 or so. And that still stands. And so we developed this New York plan. Then we did one for California, brought that to the governor. Governor of California adopted a 50% renewables law within 2 months after we met.
Yeah. So to great effect, to great impact.
Yeah, it started having impact. And so this is, well, so you can see, first of all, so these two states suddenly were we're adopting this plan, and our, well, it was not because of me, it was because, I mean, we were developing the plans, but it was because we had this group that combined science, business, culture, and community.
Messaging
and it was to be able to get the information out to large numbers of people and to a lot of the right people. You needed this coalition of people, a diverse coalition of people across.
And it was unapologetically on the left of the political aisle.
No, not well. It was. I mean, I think most of the people were on the left. However, it appealed to the far right as well, because there were a lot of. Because I mean, first of all, I was not thinking of it as left versus right. I was thinking this is beneficial to everybody because it creates jobs, saves consumers money, reduces health problems, reduces climate problems. This is beneficial to everybody. And a lot of people on the far right were very interested in, because there are a lot of people who want to own their own power. There was, in fact, this group called the Green Tea Party. So it's part of the Tea Party, which is very extreme right. But some of them really like this because they could, solar on their own roof. They can own their own power. They don't have to worry about the government controlling their power. So there are a lot of people. And then plus, wind and solar, even today, I mean, 9 of the 10 states with the most wind as a fraction of their electricity production are all red
Republican
states.
Yeah.
Because it's so cheap. Same with solar.
They're the fastest growing. Texas is now eclipsed California for solar installations.
Yeah. So it did start, I mean, certainly activists and actors are generally on the left.
But it was perceived that way. I mean, the Green New Deal, the whole thing felt like a left political block.
Yeah, before the Green New Deal was announced. So what happened though was, we got these 2 states, and then we developed plans for all 50 states, and then because we just automatized it, I just automatized it and got developed these plans and got all 50 states published, and all of a sudden now it was the presidential election. And because not only our solutions project, which we started in 2011, it didn't become a formal nonprofit until 2013, but they engaged all these other nonprofits. So we had like 100 nonprofits supporting 100% renewable energy. I went to Paris. The Eiffel Tower was lit up with 100% renewable energy. It was like, literally.
It's the power of a big idea.
Yeah, it was because this thing had just spread like wildfire to all the nonprofits in the world.
Do you think other scientists, academics, people with the tools of a place like here, Stanford, at their disposal, should dream bigger, should think bigger, should aspire to exactly what you're describing, a big affirmative, goal, statement, purpose, and as a sort of, would the world be a better place if more people took, direct action like that?
I think on topics such as this, on climate and pollution, on large scale topics
where the threat is real and existential.
Yeah, the threat is real, and you can actually, and it's a difficult problem to solve.
But does that then open up critique of science, or is that the risk of that trade?
Well, I think you do have to tread carefully, because I think of myself as I'm educating the public, and that's my job. So I don't think of myself, I'm not an activist. Some people call me an activist, but that's not what I am. I mean, I'm developing plans. My purpose is to solve problems. Like our plans, when I did that paper in 2008 on examining different solutions, nuclear power was not included. Now people say, oh, I just, since then, I say we should go for wind, water, and solar and not nuclear. And people say, well, you just don't like nuclear. No, it's because scientifically I showed it's not very good. And so that's the difference, is I actually have shown that that's not good through scientific
Yeah,
through the
people are pretty
scientific
upset
method.
by the anti-nuclear.
Yeah, and people who think they don't want to call you an activist to criticize. And so that kind of gets to where the critics of 2017 come in. But one more thing before I talk about that. So we did this 50 state plans, and then the 2016 election came up, and I got and this got out to all the presidential candidates. I mean, so Hillary Clinton, she adopted 100% renewables as her platform. Martin O'Malley adopted 100% renewables as his platform. Bernie Sanders adopted 100% renewables on his platform. He put on his website our plans from our 100% renewable energy plans was right on his website. He called me. He asked me, like, if he was thinking this was after he lost the.
Did he just call you out of the blue?
Yeah.
Did you pick up your phone?
I
and
saw
it just
Burlington,
said,
Vermont on my phone.
That's amazing.
Yeah, I remember that. I remember looking at my phone. It said
You're like,
Burlington,
who is
Vermont.
this?
Well, I think I got a warning from one of his staff members that he was going to call me. So it wasn't completely, but I didn't know when he was going to call. But we talked for about 45 minutes, and this was after he lost the primary, but he thought Hillary Clinton would win the election, and he thought he was going to then be the head of the Senate. So he wanted to propose legislation for the U.S. to go to 100% renewables in the Senate. So he was asking, do I believe this will work? Basically. And I said, yeah, I believe it'll work. And I think, it's technically and economically possible. There's just social and political barriers. And I asked him, the funny part was I asked him, well, do you want me to give you suggestions about what law should be like, what you should include to get this? And he goes, no, that's my job.
It's like hard no.
Yeah, it was hard no. He said, he's like, he wanted to know it to work, but policymakers want to put their stamp on the actual legislation. Yeah. And that was fine with me. I offered. But he did say, he said he wanted to do other things. So not only introduce 100% renewable legislation, but he said, let's write something together. And even though Hillary Clinton lost the election and he wasn't head of the Senate, he did introduce 100% renewable legislation to the Senate. In fact, there were 8 laws and policies, including the Green New Deal, which are the last 2, that were 100% renewable laws and policies proposed in the Senate and the House. And then we did actually write an op-ed together on the next year after his proposed 100% renewables law was introduced. But okay, so that, with all that in mind, so we were getting a lot of traction with these 100% renewable plans. And so we had a big target on our back because there are a lot of people who don't like just renewables. They like nuclear power, they like carbon capture, coal, natural gas, oil, with or without carbon capture. They're bioenergy people. We were very strict about what we were including because we want to solve these problems effectively and quickly and with the most health benefit, most climate benefit, most energy security benefit. And we did not want to include these other technologies.
All of the above.
Yeah, it's not like,
explicitly not all of the above.
Yeah, so the Obama administration had an all of the above policy, which was let's try everything, hope something works. And that was basically, Republican and Democratic administrations have had similar things with different degrees of, favoring different technologies. But we were like strictly, let's just use clean renewable energy, no combustion, focus on health.
Don't burn things. Burning things is largely the problem. Air pollution, and that's the thing. Let's stop doing
burning things
that.
is the main problem because you're releasing greenhouse gases and air pollutants, and filters just don't work that effectively. So there are a lot of people who didn't like this, nobody was listening to them because there were scientists who, and not only scientists, but, advocates and policy people too, who, they had their own plans, but, we had so much momentum and so many people had agreed with, let's do this, that they weren't being listened to. So they thought, well, okay, a couple of them banded together and they got other disgruntled people together. And they thought, let's write a paper to just ruin their credibility. And that's what they did. They did in 2017, this group of 21 people wrote a paper with the sole purpose of trying to destroy our credibility, to assassinate our characters in terms of scientific character, scientific credibility.
Yeah, their claims were like poor assumptions, poor modeling, I mean, it was a scathing.
Yeah. And, and to be fair, like, some of their criticisms are, reasonable. They're not like, there's a lot of uncertainty in there.
Can you steelman their argument? Like, what elements of their arguments were helpful and constructive? Were there any?
Yeah. So, just to put everything in context, so they wrote this. Well, they wrote because we had published a paper in the Proceedings of the National Academy of Sciences, which was on top of getting all this information out and doing a 50-state plan. After we did the 50-state plans, we then did another study, which was we call a grid integration study, looking at, if you actually simulated in time, and we did it at 30-second time resolution, a system with 100% renewables in the United States, can you keep the grid stable at low cost? And so we did a paper on that and found that we could. And I used the model I developed, the weather prediction climate model, to predict the winds and solar radiation fields throughout the United States every 30 seconds for 5 years to develop fields of wind and solar that we can then, combining with everything else, storage and hydro and other technologies, can we keep the grid stable? And I found, yes, we could. and it was a very detailed study, and it was published in this really prestigious journal. And then we got an award from the journal for being one of the top 5 out of 16,000 papers submitted.
Wow.
that year. It was it was a very prestigious prize. And
they're like, here's an award, now here's a complete takedown.
Yeah, so on top of after getting the award, then this group was steaming because they didn't like the fact that everybody was listening. We had all these people listening to us and actually trying to address the problems with the solution, ignoring what they were proposing was, let's use nuclear power, let's use carbon capture, let's use bioenergy, or let's just do all of the above. And so they were steaming and really wanted to knock us down. But usually when you submit a paper and somebody has a critique, they usually submit it as a letter, which called a letter, which is not a full paper. It's a letter, and then you get a chance to respond to that letter. But
that's the etiquette. That's the convention.
That's the standard way to do it. People don't write papers because paper requires new science. And when you're criticizing somebody else, there's no new science there. All you're doing is criticizing, and which is fine. And you can criticize, but it's not a paper. It's a letter. It's just by definition, by the journal standards, it's not a paper because that requires new research. And so they wrote it as a paper and submitted it. Didn't tell us so then 2 of the people on the paper of the 21 were from Stanford, where I work. And 3 of them were for Stanford. 2 of those 3 were on the PhD dissertation committee of one of the students on one of our papers. None of them told us they were writing this paper. None of them told their students they were writing this paper, even though 3 of them worked right nearby. So they were keeping it secret. Didn't tell us anything.
Oh wow! So it was full. Yeah.
Yeah. They didn't tell the students that they were mentoring. The ones who were the advisors didn't tell the students that they one student they mentored anything about it, kept it secret, and then got it ushered through the Proceedings of the National Academy of Sciences, PNAS.
So there's bad blood here. I mean, it feels the whole thing you're kind of getting little glimmers of activities and things that.
No, I had no clue.
Well, after the fact.
Yeah, after the fact.
After the fact, you start piecing together some. Yeah. Okay.
Yeah. Well, after the fact, there was a lot of stuff came out, but anyway, they ended up publishing it as a paper, and then they issued 2 press releases to try to disseminate. And it was there were some reasonable comments, but the ones that I got really upset were the critiques of the modeling. They just out of the blue, they would say, we had modeling errors. Now, just to give you an idea, it wasn't we had no modeling errors whatsoever in this paper. You can argue about the assumptions of the models, and that's not what they were talking about. They were talking about we had modeling errors, that we had made mistakes in our model, there were bugs in our model that caused figures to be erroneous. And just to give you an idea that it was not our errors, it was their own errors in simple errors, really, I don't know, for lack of a better word, dumb errors. Like, for example, we had a table that had values that were average values. And it's obvious they are average values from everything in the paper. And the source of the data is clearly reference to another paper which says they're average values. They claimed that these were maximum values, that they weren't average values, they were maximum values. And then as a result, all our figures were wrong because the figures don't make sense if they're maximum values.
Yeah.
And then they published this as a modeling error when it was their own error for trying to claim these were maximum values instead of what they were, average values. And so they claimed that was a modeling error, it was their own error. And so I had 4 experts write statements saying these are average values.
Because this became a legal thing.
Yeah. They refused to correct these clear errors, their own stupid errors. I mean, this is just so mindless. You can't here's 21 people claiming to be expert scientists, and they can't even understand the definition of values in a table.
And you felt this wasn't just an attack on you and the team involved in the paper, but on the broader project and on the broader imperative to more quickly advance.
Oh no, this is what their purpose is. That's why they issued 2 press releases. They wanted to get headlines, and they did get headlines saying horrible things that Stanford professor's work contains modeling errors. Like nothing. This whole idea of 100% renewables is based on a lie.
Yeah.
That's like a headline.
Yeah.
It's based on erroneous information. It's just based on poor science, like that kind of stuff. And that's what they got. And so that's why it was just, they would refuse to correct anything. They refused to back off. To this day, they still haven't corrected anything, even though experts have shown that what they've claimed is nonsense. And it is. It's really, I mean, it's.
But you sued, right? I mean, you took it to court.
Well, I first tried to get them to correct it. I first tried to get the journal to correct it. I tried to get my university to get them to correct it. Nobody wanted to do anything. They just said, "Oh, because we did respond in the journal as a letter to their paper." And so they said, well, you've been able to respond to them. That should be enough. That's basically, they said what they wanted. You said what you wanted. But they had all these headlines that influenced how people perceived our work and behaved in it. And that had a lot of consequences to the students. One of the students left academia altogether, devastated, and it's embarrassing to, the students. And it was really a humiliating experience when somebody, could just try to ruin your credibility with complete trash. I mean, it was junk science being published in a legitimate journal, and it wasn't even science. It was just, it was just a smear. It was a smear piece. And on top of that, one of the editors, when I submitted to the journal PNAS, I'd submitted them a list of things I'd asked them to correct before they published their paper. And so they said, okay, we'll send these off to the authors to have them consider correcting them. And it turns out they never sent those. For 2 months, I thought they had sent these requested corrections, and the journal never sent them. And so 2 months later, they sent me a revised version of their paper that they were going to publish. And I said, well, there's no changes here. And then the person I was communicating with says, well, we sent it to the editor who was going to send it to them, but it turns out he never sent them. He never sent the corrections, which leads me to think, okay, well, this is clearly, he was doing this intentionally. It might have been the editor who was trying to push this through to help, ruin our credibility. I mean, I don't have evidence of that, but it was like, that's what it's felt like.
What do you feel? Because, without all the context, somebody sees, Stanford professor sues National Academy of Sciences, and it's like, whoa, what that's not the scientific method. It's kind of the quick vector of attack against that is like, where isn't critique allowed within science, and why was like that there's concern around the integrity of the scientific enterprise was part of the reaction to that. Did you feel that? How did you grapple with that?
Yeah, well, that was part of the smear campaign in the misinformation campaign, because in fact, they use this in the court. They basically tried to say that, oh, this is a scientific disagreement. But that's not what the experts say. The experts call these false facts. I mean, there's a scientific disagreement is when there are, like, what's the impact of climate change on the Earth 20 years from now? Some people say this, some people say that. That's a scientific disagreement. Whether the value in a table is an average or a maximum value, that's a question of fact. That is not a question of science. That's a question of fact. So they're confusing scientific disagreements with questions of fact. And when a fact is false, and it's either intentionally false or false with reckless disregard for the truth, that's called defamation.
Yeah.
And that's what I sued for, defamation for three or four specific false facts. And they've been trying to claim, oh, this is just a scientific disagreement. Well, that's because they're using the false definition of a scientific disagreement. If they think that, whether a table has average or maximum values is a scientific disagreement, that's because they do not understand what a scientific disagreement is.
Yeah.
And that's the problem and everybody who wanted to support them, which is people who were against clean renewable energy only, those people would continue this false idea that this is a scientific disagreement. It's nothing to do with scientific disagreement. The things that I disagreed with that are scientific, I put in the reply to them. And so those are very clear.
Well, it's so fraught. I mean, the stakes are high because it's not, the stakes aren't the paper, or the stakes aren't even the lawsuit. The stakes are ideas for the future.
Right.
And they're not just ideas, they're real, because there's, with you as an example, a long history of affecting great impact on policy, on trajectory of the energy system. And so there are real stakes, and then there's humans sort of caught in the middle of what is basically a battle for the future.
Yeah, well, it was clearly a mechanism that they wanted to try to get their information out. This was a way for people who weren't getting heard to have people, oh, listen to me. Mm-hmm. I mean, it was obvious. In fact, the lead author, I mean, he did this, and he'd say, like, because we had like our paper would get published, and then they'd have some famous actor or actress tweet it out, for example. Right. And then the lead author of this paper would say, oh, so and so, why don't you tweet my paper too? I mean, he literally said this. This was people who weren't getting attention, and they wanted to bring down people who were getting attention. Yeah, and that's basically what it was.
It's unfortunate.
Yeah, it's kind of pathetic because it could be more constructive, but anyway, it is what it is.
What do you think about the idea that? With regards to what's getting deployed where in the here and the now, whether a nuclear project is going to be moving forward with investors and permits and all that, or a series of solar and wind farms, that the market is going to decide that, and the market is in a pretty good place with respect to that decision. Like, it is firmly choosing wind and solar and natural gas to some degree, but mostly wind and solar in terms of new cumulative capacity installations in the US and Europe, in China. There's more investment in solar last year, I believe, for the first time, than total investment in fossil fuels, period, globally. That the market has decided, and that the market is moving in the direction of your paper, of your viewpoint, that essentially validating what you've been saying, the market is moving that direction.
Yeah, that's the good news, because my goal all along has been to try to solve these problems, and it's just so lucky that the solution is actually implementing itself. Now, I have to say, though, it's slower than it needs to be, but it is going in the right direction. And wind, solar, batteries, electric vehicles, heat pumps, electric induction cooktops, these are moving off the shelves and going and being deployed on a massive scale. I mean, at the end of this year, China, as you mentioned, they'll have 500 gigawatts of solar installed, and that's more than the rest of the world combined, I believe. And within 3 more years, they'll have a terawatt installed, so another 500 gigawatts. I mean, they're moving at a massive pace, but every country is going rapidly in the electric power sector. I mean, but we do need, the main sectors are electricity, transportation, buildings, and industry. And we do need transportation to move faster. They're probably maybe somewhere between 25, 30 million electric vehicles in the world, but there are 1.4 billion vehicles overall that we need to transition. Buildings, we need to get rid of gas and oil and wood in buildings and electrify those. It's just straightforward in concept. We can certainly all new buildings can be renewable, and same with new vehicles. But we have to retrofit existing vehicles. In industry, we need to electrify that as well. Probably the hardest. But we have the technologies: arc furnaces, induction furnaces, resistance furnaces. These are all electric technologies for high temperatures. So it's really a combination of the market, but we need strong policies to be put in place to speed it up even faster.
Yeah, what is your view on, roughly dimensionally, how fast it is moving and how fast it needs to move?
It's
like, what is the timeline and how?
Yeah, well, we need 80% transition by 2030, so it's not close to that rate.
But that number, where does that number come in your mind? I mean, I know that there's IPCC reports and things of that nature, but what is the hard and the fast of that number? Like, what happens if we don't get to 80% reduction by 2030?
Well, so in terms of air pollution, we need 100% by today, because every year 7.5 million people die. And so if we eliminate all air pollution today, those deaths go to basically 90% reduction of that. So only 10% of that, because there's still natural air pollution that causes mortality. So that we can eliminate air pollution right away. And that's on one end, that's tugging. We need a rapid solution there. From a climate point of view, if 2030, we need 80%, not only in electric and energy, but also all emissions, because to avoid 1.5 degrees Celsius global warming, we're at about 1.1 to 1.2 right now since the 1850 to 1900 period. And because we're not doing any carbon capture, which is not helpful at all, because, I mean, in my opinion, carbon capture just increases CO2 because it's an opportunity cost. Every energy, even a renewable energy powering it, could reduce more CO2 by just replacing a fossil plant. But so we need a rapid emission reduction, 80% by 2030 and 100% by 2035 to 2050 to avoid 1.5 warming.
So those are the goalposts.
Yeah.
I mean, 2030 is 7 years from now, or even a little bit less. It's pretty close. So, I mean, it doesn't even necessarily seem possible to manufacture that much solar and wind and put it in the ground over 7 years to get to 80% global reduction. I mean, it just seems like there's tremendous growth, and there's exponential growth, geometric growth, whatever word you want to use, around all of these things. There's declining cost curves. There's a lot to be hopeful around with respect to the rise of renewables and electric vehicles and energy efficiency and just all manner of things, but it's not fast enough.
Yeah. Well, we spend $11 or $12 trillion a year on all energy. That's across all energy sectors. And to transition, we need about $62 trillion worldwide. And so
there's a little over $1 trillion a year, according to Bloomberg, in all of these renewable, clean, green technologies, right now, including electric vehicles.
Yeah, but if you look at what everybody pays, so it's not only investment, but what people pay for all the energy, it's on the order of 11 or 12 trillion. So if that was moved, first of all, to not investing in any more fossil fuels or nuclear or bioenergy or anything else, or fossil vehicles, or we're talking about all energy. We could actually generate the capital we need to do this, to actually transition. But the savings are so enormous. I mean, think about it, because in 2050, the cost will be about $17 to $18 trillion per year. But if we electrify all energy, our energy requirements go down about 56% because of the efficiency of heat pumps, efficiency of electric vehicles, efficiency of electric industry, eliminating all the energy needed to mine, transport, and refine fossil fuels and uranium. It's about 11% to 12% of all energy. And end-use energy efficiency, we can get down 56% of energy requirements, plus the cost per unit energy is about 15% lower for clean renewables than like wind and solar compared to fossils. So,
and that big reduction is like driving a car, the total energy of the fuel, only a small fraction of that gets used in the engine to actually move the car forward 20% or something like that.
Yeah, only about 20% of the energy in gasoline goes to move the car.
But with electric, there's an extremely high efficiency of use of the primary energy.
Yeah, the electricity going into your car, about in the order of 80% goes towards moving your car, and the rest is waste heat.
Yeah, so there's a factor multiple of efficiency gain throughout the system if everything electrifies, even including transmission losses.
Yeah, there's a huge reduction of energy demand and going to electric vehicles. Same thing with heat pumps. Heat pumps use 1/4 the energy as natural gas heaters, so because they just move heat rather than create heat.
Yeah.
So those are the two main things, and then there's some in industry. There's some electrification improvements, and then getting rid of mining. That's about 11% to 12% of all energy worldwide.
It's for mining.
And so we calculate 56% reduction of demand just by going to electricity and wind, water, solar providing the electricity. And then so that means that even if the cost per unit energy is the same, you're using 56% less energy. So your annual costs are 56% lower. Mm-hmm. But in fact, the cost per unit energy is going to be less. It already is less with the wind, water, solar. Yeah. We calculate about 15% less. So that's about a 63%.
Almost no marginal cost to run. So
there's no fuel cost at all.
It's deflationary. It's why it's the primary principal component of the Inflation Reduction Act, is because these things are fundamentally deflationary.
Right. But so if we spend $17.5 to $18 trillion per year on energy in 2050, and you go to wind, water, solar, we're ending up spending $7 trillion per year. So that's about $11 trillion per year savings. So if our capital cost is $62 trillion and we're saving $11 trillion a year, that's a payback time of 5 to 6 years, just in the energy. Health cost savings are another $30 trillion a year. Climate cost, another $30 trillion a year. So the social cost payback time is less than 1 year. So if we transition our energy system to 100% wind, water, solar across all energy sectors, when you account for health and climate cost benefits in addition to energy cost benefits, the payback time is 1 year, so if we galvanize society to actually do this, there's little downside to doing it as fast as possible.
Yeah, the air will be cleaner. The effects, the ravages of climate change will be substantially mitigated. The risk for future generations, it's economic. I mean, in almost every instance where wind and solar goes in the ground today, it's the lowest cost option, even without subsidies, even though subsidies are important. And subsidies are used in every form of energy is maybe another thing to just touch on for a second, because people like to rail against the subsidies that renewables need or the subsidies that electric vehicles need, but it's the case that every single form of energy has been subsidized throughout our global system from creation until still.
Yeah, that's true. All energy has been subsidized.
It's foundational to national progress. It's food systems are subsidized as well because it's foundational. So it's
right.
Well, this has been fascinating. I really appreciate your time here and jumping into your story. I find it fascinating. I find it inspiring. You've been a hero to me and to many in terms of the impact that you've had. Your research, you've truly made a big impact in the world of climate and clean energy. And I've been observing it from afar since graduating from here, but it's just nice to reconnect. It's nice to chat about some of this with you in person. I know some of it's probably pretty difficult too. I mean, the stuff we were talking about with the National Academy of Sciences were probably very personally taxing for you, which I can't even really imagine.
Yeah.
But I appreciate you opening up about all of that. And I guess I'll leave it with just one more question, which is, are you hopeful for the future?
Yeah. No, I've always been hopeful and still am hopeful because I know we can solve these problems. I know we have the ability to solve the problems technically and economically and socially to a degree. I mean, there are barriers, of course, but we will eventually transition. It's really, in my mind, just a question of how fast. So a system, I mean, if I look 100 years from now, a system, we won't be burning fossil fuels in 100 years. So that's too late to transition in 100 years. But so there's some time between then and now that we will transition. And my job is to try to look at the science to show, okay, what are the benefits and costs of doing such a transition more rapidly, and then trying to educate the public and policymakers about those choices. But so what I've worked on so far and looked at so far, I know it's possible. So, and I know it'll be beneficial, and it'll actually solve the problem that I set it out to solve when I was a young kid. So that would make me gratified if that ever happens. But it's I'm really would be gratified for humanity, because all the lives saved and the devastation that we've avoided by such a solution.
Yeah.
So,
time is of the essence.
Yeah. Every year that goes by, we lose more time and people.
Yeah. Well, thank you for all the work that you do, Mark. Keep up the good fight.
Well, thank you, Ted, for your interest, and for you. Thank you for joining our program and having the passion to go through it.
That was a big deal for me personally to get into this program those years ago. I was, wow, I'm going to this illustrious place, and it's a pretty special program. So,
thank you for being part of it.
Yeah. Well, we'll leave it there. Thanks so much, Mark.
Okay, thank you, Ted.